Hi everyone. In this video we're going to look at nuclear fission and examine some of the properties of the energy released by fission. We also will be looking at nuclear fusion. So to begin, I've kind of highlighted one of the more common nuclear fission reactions between uranium-235 plus a neutron will yield barium-141 and krypton-92 plus 3 additional neutrons. So the way nuclear fission works, although I'm simplifying quite a bit, you take a uranium-235, which normally doesn't undergo radioactive decay very often. We learned last time that was every 708 million years or so. But if you send a neutron into the nucleus, if you really get that neutron going up to high speeds and then you fire it into the nucleus, that much energy just completely creates an unstable nucleus and it will split into two. And that split should yield energy. And we're going to see here how much energy it yields. So I've gone ahead and I have put together I guess I've gathered the numbers for the atomic masses of each of this or chemistry would be like reactants and products, but I guess we'll just call it the things initially and the things afterwards. So we have initial minus final to find kind of, how much did we have to begin with. We'll subtract how much we had left over, and we're going to see if there's a big difference there. So when we do that, we can kind of, maybe you can try to do the calculation. I mean, this here would be the initial mass, and all of these combined would be the final mass. And it turns out that when you subtract the two, you'll get about 0.186032 atomic mass units. And so when we multiply that by the 130 or 931.5 mega electron volts, this amount of atomic mass units equals about 173.3 mega electron volts. Okay, so next we kind of want to say we need to put this in relevant terms. Okay, so because sometimes even if I look at 173.3 mega electron volts, it doesn't really mean all that much. So what we'll do is we'll use a little bit of our chemistry to establish a few things. So let's take for this 1 kilogram of uranium-235. So if we kind of remember from chemistry, we have the number of moles is equal to the mass divided by the molar mass. Okay, so what we want to do is understand that we have we're going to find out the number of moles. So we're going to take 1 kilogram divided by the molar mass of this uranium-235, which is going to be this number right here. That represents the molar mass. Oh, 43930, and I'm pretty sure that when we do that, we get roughly number of moles is going to be equal to 4.255 moles. Okay, so, this is, yeah, for chemistry, you do it in grams. So it's 1,000 grams for 1 kilogram, so you get 4.255 moles. Okay, so then what we want to do from there is understand that the number of uranium-235 atoms within a kilogram. Okay, that's that Avogadro's number is going to help us there. Okay, so that's 6.022 times 10 to the 23. So within 1 mole, there will be 6.022 times 10 to the 23 atoms. So we have 4.255 moles. So I'm going to times that by 6.022, 14 times 10 to the 23. And so I end up with the number of atoms through Avogadro, the number he came up with for number of atoms in 1 mole is going to be, for our 4.255 moles, 2.562 times 10 to the 24 atoms. Okay, so this is where the fun begins, because there's that many atoms in a kilogram. If a kilogram of uranium goes through fission, then each one of those atoms supplies 173.3 mega of electron volts. So now we're going to times this by 173.3 mega electron volts, and we will get 4.441 times 10 to the 26 mega electron volts per kilogram. Okay, so that's 4.441 times 10 to the 32 electron volts per kilogram. Just getting rid of the mega. And then we can then go from electron volts to joules. So then I believe we say in order to do that, we times by 1.60 times 10 to the negative 19. Yes, we do. So we times by 1.6 times 10 to the negative 19 joules per electron volts. And then what we're going to end up with is 7.10 times 10 to the 13 joules per kilogram. So for each kilogram of uranium-235 that undergoes nuclear fission, you'll receive 7.1 times 10 to the 13 joules per kilogram. Now, again, we need something to compare to, something that's relative. So for comparison, 1 kilogram. So 1 kilogram of uranium-235 would produce this many joules. 1 kilogram of gasoline produces 4.4 times 10 to the 7 joules. So a kilogram of uranium compared to a kilogram of gasoline produces around 1 million times more joules. 10 to the 6 is the difference here. More energy than a kilogram of gasoline. So I think that puts it in perspective for the amount of energy that nuclear fission releases. And now finally, what we want to look at, just briefly, we'll look at nuclear fusion and we'll look at the nuclear fusion that occurs within our own star. So the nuclear fusion reaction that occurs kind of looks a little bit like this. And for a long time, you said, you take a couple hydrogen, you fuse them together, you get helium, and that's a very kind of simple way of putting it. There are kind of steps to the nuclear fusion reaction, and the first is, get enough hydrogen to get a good gravitational pull. But in terms of the process, you have two hydrogen atoms, so they're two H11. That's going to form, if you squeeze them tight enough, H21 plus a beta particle plus a neutrino. Okay, so that's kind of that process to begin with. And then the second step is going to be H11 plus the H21 that just was formed, and that will create, you squeeze them tight enough together, just kind of a simple helium 3,2 plus a gamma ray photon. After this occurs, you take two of those helium 3,2s, that's what we say is happening inside of our star. You squeeze them together, you'll get 4,2 helium. You get a helium 4 atom plus 2 hydrogen atoms here, plus some more gamma ray photons. Okay, the last little step here is that essentially when this happens twice, it produces 2 positrons. So those positrons combine with some electrons floating around, and they annihilate. You get 2 extra gamma ray photons. So that's kind of the nuclear fusion process, highlighted there. Sometimes it's referred to as a proton-proton chain, but essentially it's a little more complicated than just smucking two hydrogens together. There's a bit more of a complicated process, which I guess we can now say, because we looked at all of that radioactive decay in the last lesson. So it's kind of how the fusion process works. That being said, that's where we'll end this video. A little bit about fusion and a lot more about nuclear fission. So yeah, I guess the last piece is going to be for our lessons here in physics. We're moving into some even more strange things that we figured out about the nature of matter.